Hi everyone, thank you for joining us. This video is intended to give a summary of a recent work by our group where we rationalise the influence of the synthesis solvent used to prepare conjugated microporous polymers on their resultant porosity. If you have any questions following this, please feel free to either contact us on Twitter using the handle @ambuild2 or through the email address on the slide. For about 10 years now, it has been known that the choice of solvent used to prepare CMPs has the ability to affect the surface area of the resulting polymer. However, until recently there has been no in-depth analysis as to how it can do this. As part of this work, we have found that the trend between CMP porosity and the polarity index of the solvent, which, as the name suggests, is a standard measure of how polar one solvent is in comparison to others, is dependent on two factors. Firstly, the dipole moments of the two monomer types with respect to each other, and secondly, whether or not hydrogen bonding groups are present and are able to interact with the solvent. Before delving into the work itself, we first need to introduce a few things, beginning with what CMPs are for those who don't already know. CMPs are a class of amorphous microporous organic polymer with a fully pi-conjugated skeleton. Due to the variability in synthetic strategies and monomer building blocks that can be used to prepare these materials, they have a range of potential applications, from electrical energy storage to heterogeneous catalysis and gas adsorption. The CMPs we have studied as part of this work, which have all been prepared by a palladium catalysed Sonogashira-Hagihara catalytic reaction between 1,3,5-triethynylbenzene, which we've called TEB here, and an aromatic dibromo monomer, which we've called a DBM, were first synthesised by the Cooper Group in 2010, being prepared in 4 solvents of varying polarities: DMF, toluene, THF and 1,4-dioxane. As we mentioned earlier, until now there has been no real investigation into how the solvent choice can influence the growing polymer network, despite the fact that in the materials we're studying here, we saw that the solvent used can increase the BET surface area by as much as 720 metres squared per gram. The initial solvent used to prepare CMPs with was toluene. However, this has since been replaced by DMF due to the fact that CMP networks prepared in DMF appear to yield networks with higher BET surface areas, which is believed to be due to the fact that the networks made in DMF have a greater proportion of micropores compared to those prepared in toluene. Due to the expensive palladium catalyst used in this synthesis strategy, it is clearly important to find a method of choosing the solvent that will yield the CMP frameworks with the highest possible BET surface areas, which will in turn reduce the need for solvent screening in future. We believe that the reason CMPs prepared in different solvents give different surface areas is due to the miscibility of the two monomers within the solvent. To test this, we plotted the polarity index of each of the 4 solvents studied in this work against the microporous surface areas of the CMPs in each of the solvents. We then calculated the dipole moments of each dibromo monomer used, along with the coupling partner TEB, using Gaussian geometry optimization calculations. Based on the results of these calculations, we saw 4 distinct trends between the polarity index of the solvent and the microporous surface area of the CMPs. Each CMP studied was classified according to which of the 4 trends it fitted and assigned to Group 1, Group 2, Group 3 or Group 4. We will now go through each of these groups in detail. We begin with Group 1. This grouping consists of dibromo monomers with no nitrogen functionalities and an absolute difference in the dipole moments of the two monomers of less than 0.1 dBi. This small difference in the dipole moments of the two monomers suggests that they are of very similar polarity and should therefore both be miscible in the same solvents. The approximate trend we see for group 1 is that as the solvent becomes more polar, ranging from toluene at 2.4 to DMF at 6.4, the microporous surface area of the CMP materials increases. This can be explained by considering the miscibility of the reactants in each solvent. In toluene, both monomers are very soluble and as such are fully miscible within the solvent. In DMF, however, which is the most polar solvent we have studied, we see the opposite occurring, with both monomers being immiscible within the solvent, leading to co-phase separation of the reactants from the solvent. THF and 1,4-dioxane, which have polarity indices between those of toluene and DMF, act as intermediates here. We can therefore say that for group 1, DMF acts as an anti-solvent, allowing polymer formation to occur only in regions of low solvation. We have chosen to plot DBM4 in its own category here, group 2, as it does not properly fit into any of the other three groupings. Like the group 1 materials seen on the previous slide, DBM4 has no nitrogen groups. However, unlike group 1, it has a significant difference in the dipole moment between the two monomers. Despite this, the aromatic nature of DBM4 means that the trend seen here can be approximated as following that of the group 1 materials, in which the microporous surface area of CMP4 increases with the solvent polarity index. Group 3 also consists of just one CMP material, in this case CMP9. DBM9 has a high dipole moment due to the attached nitro group. Here we see an increase in the microporous surface area of CMP9 as the solvent polarity index increases from toluene at 2.4 to 1,4-dioxane at 4.8. However, on further increasing the solvent polarity to that of DMF at 6.4, the microporous surface area of CMP9 drops. This suggests that here 1,4-dioxane is acting as the antisolvent, where both monomers are immiscible within the solvent, leading to co-phase separation. The final group, group 4, consists of CMPs 10 and 11, each of which has a DBM containing an amine group, which again gives rise to a large dipole moment difference between the DBM and TEB. Here we see the microporous surface areas of the CMPs increasing with solvent polarity from toluene to THF, before decreasing at 1,4-dioxane, and then subsequently increasing once more at DMF. Both CMP10 and CMP11 show their lowest microporous surface areas in toluene, as whilst TEB is soluble in the solvent, the DBM is too polar to be fully miscible, leading to phase separation. As the solvent polarity increases to that of THF and 1,4-dioxane, both DBMs become more soluble than they were in toluene, whilst TEB becomes less soluble than it was in toluene, leading to partial co-phase separation, with THF showing the largest co-phase separation. When preparing these CMP materials in DMF, however, the microporous surface area of these two polymers increases rapidly. Whilst we would expect these two materials to show the same trend as is seen for group 3, where the microporous surface area decreases on increasing the solvent polarity to that of DMF due to the insolubility of TEB within the solvent, we don't see this here. We believe the difference must occur due to the functionality of the DBM. DBM9 in group 3 has a nitro functionality, whilst DBMs 10 and 11 contain amine groups. We hypothesize that the amine groups on the group 4 DBMs may be able to interact with solvents containing oxygen, such as DMF, via hydrogen bonding between the amine group of the DBM and the oxygen atom of the solvent. DMF is known to form cluster structures that we can postulate are able to template the CMP network formation, leading to the increase in surface area going from 1,4-dioxane to DMF. The figure shown on the slide shows our postulated phase separation behaviour for TEB, which is shown in pink, and the DBMs shown as green circles for each group in each solvent. The group 1 and 2 DBMs are fully miscible in toluene, partially co-phase separated in THF and 1,4-dioxane, and fully co-phase separated in DMF. Group 3 DBMs are fully phase separated in toluene, partially co-phase separated in THF, fully co-phase separated in 1,4-dioxane, and partially co-phase separated in DMF. Group 4 DBMs are fully phase separated in toluene, partially co-phase separated in THF, partially co-phase separated in 1,4-dioxane to a lesser extent than in THF, and fully miscible in DMF via hydrogen bonding between the DBM and DMF. The relative surface area of the resulting CMP network is highlighted by the surrounding box, with low surface area in red, medium surface area in orange, and high surface area in green. We can now draw some general rules from assessing the overall postulated phase separation behaviour we have seen. Firstly, each group must be considered individually. Secondly, the highest surface area of the CMP network for each group results from co-phase separation of the reactants. Next, the lowest surface area results when TEB and the DBM are kept fully apart. And finally, interaction between the solvent and reactants can influence the surface area of the resultant polymer. To summarise, our work has rationalised the trends seen on preparing a selection of conjugated microporous polymers in solvents of differing polarities, allowing us to demonstrate a link between the miscibility of the reactants within the solvent chosen, the resultant phase separation behaviour, and the microporous surface area of the polymer framework. We then came up with a set of general rules which we believe could potentially be applied to different amorphous hypercross-linked materials to aid in the development of new CMPs for energy storage with even higher surface areas and micropore volumes in the future. Thank you again for watching this video. We invite you to ask any questions on our Twitter page using the handle @ambuild2 or by contacting Dr. Abby Trewin using the email address on the screen.